Hello, everyone. Welcome to the late October. Is it October? Yeah. Late October edition of South Bay Systems, everyone's favorite talk series if you live in the South Bay and not San Francisco, in which case you might have a locality bias in a different direction. We are a nonprofit independent talk series and also sometimes occasional coffee chats. We have no affiliation to any company or product. I think many of us are employed by companies that may or may not supply products, but there is no such affiliation with the talk series. Monthly-ish, with exceptions, maybe twice a month, maybe if it's October or something like that. And we're focused on system programming for a very broad definition of systems. This is us. Here's some people. I'm on the slides there. There I am. Hello. Here are some previous talks that we gave. We had John Osterhout. We're talking about a replacement for TCP. We had Hannes talking about how great DuckDB is, which you all already know because you're all probably database people. We have Bauplin talking about the awesome design patterns there, and you got your boy Andy, database tuning. We need more people to give talks always, so please, if you would like to give a talk in any area somewhat related to systems, networking, that just has systems. Operating systems, that's a type of system. Databases, compilers, security, hardware, verification testing. It can be broadly anything. But if you're interested in giving a talk, please do so. Especially if it's not databases, because all of us organizers are database people. So it's nice to have some variety and diversity, because we can't really provide much of it. Thank you very much to Adobe for hosting. If you have a venue space for 50+ people, or you want to sponsor food and drinks, please reach out, because we don't have any money that we're going to spend on the talks. Maybe we're all just cheap. All right. Adobe.
Hey, everyone. I'm Arvind. I'm your host from Adobe. Big shout out to South Bay Systems for choosing Adobe to host their event. We're happy to have you here and do these types of technical talks and knowledge sharing. I wanted to ask people, when you think of Adobe, how many people think of Photoshop? Can I have a show of hands? Okay, cool. Wow, okay. How many people think of PDFs? Okay. So there is a business unit in Adobe that does nothing to do with PDFs or Photoshop, but it collects data from Fortune 500 companies at petabyte scale, and we build data pipelines, ingestion pipelines, query processors, and reporting capabilities on this data, which is called the Adobe Experience Platform. That's the organization that I work for, right? And we're also looking towards agentic workflows and what it means to move away from looking at websites and clicking on products to having conversations, and how that's going to reshape marketing and e-commerce. So there's lots of interesting work happening here, and that's my pitch to also say we are hiring in a variety of roles. And if you're interested in distributed systems, big data, agentic workflows, Gen AI, there's openings across the board. So take a scan of the QR code or reach out to me on LinkedIn. Happy to help there. So with that, I'm going to turn it over to the first speaker, or actually Ben, who's going to introduce the first speaker.
Thank you very much for that awesome intro. You should come work for Adobe. I say that because they sponsored our event. OK, we have 3 awesome speakers today. We have Songqiao and Raghav from StarTree. They're going to talk about the evolution of StarTree. It's a very awesome system. And we have Owen here to talk about VeloDB. He's the co-founder of the company and also a PMC member for Apache Doris. Give it up.
Yeah, good evening, everyone. And thanks to the organizers for giving us the opportunity to present the talk. I am Raghav Yadav. I'm working as a tech lead for Iceberg Initiatives at StarTree.
Hello, everyone. My name is Songqiao. I work at Tier Storage at StarTree.
Yeah, today we are going to talk about high concurrency and low latency serving on data lake. So raise your hand if you heard about, so today's agenda is basically we will introduce Apache Pinot and then high level introduction, and then we will tell us the story, how did we move from local storage to remote storage, and then we will talk about the final evolution, which is moving from Pinot format to open data format. Raise your hand, how many of you heard or worked with Apache Pinot? Yeah, so we have few people who have worked with it, Apache Pinot. So Apache Pinot started at LinkedIn. The first project which it fueled was or supported was the who viewed your profile. So anytime if you go on LinkedIn and have clicked who viewed your profile, you are hitting a query against Apache Pinot. Then Uber started using Apache Pinot, and Apache Pinot is one of the main components in real-time data infrastructure, and it is fueling a lot of their user-facing analytics. And Apache Pinot was then incubated to Apache project, and Startree was founded in 2019. And since then, this project has really kicked off. We have 5,000 community members, more than 300 contributors, and roughly 30% of the 1,000 Fortune companies are using Apache Pinot. And before we go into the high-level architecture, let's first understand the title. What does the serving mean? So traditional analytics basically give you the historical insight. So if you have used dashboards, BI dashboards, generally they are like in a week, so they will be updated in a week, in a day, or in a month. Serving basically puts an analytics into the hands of user and lets application build the user behaviors. Example would be whenever you are using any AI app or any application, and if you want to see how user behavior or user behavioral analytics, that's where serving will be used. And what do we mean by high concurrency? So imagine any application which has millions of users, and each user is kind of refreshing or understanding their analytics. So all those queries had to hit the server. And what does the low latency mean? So by low latency, what we mean is basically as soon as the event is generated by any user action, when it clicks a website or when it does a certain operation, how fast it can be queryable. So in the traditional space or historical analytics, generally it is in couple of hours or even in days. But real-time analytics databases, what they do is as soon as the event is generated, using a streaming architecture, you can query those within seconds. And that's what we are going to talk about. So let's first have a high-level architecture. So Pinot segments. So Pinot segments are the fundamental unit of storage and query. Think of it as having subset of rows or within a table across columns. And basically, this is the unit which allows Apache Pinot to shard, partition, and horizontally scale. And we have real-time servers and offline servers. And these servers are responsible or host these Pinot data segments. And basically, they manage when the segments are written and when the segments are queried. Basically, server's responsibility is to return the data from the segments. And then we have a deep store. So deep store is an external store where we store all these segments permanently. And generally, in case of disaster recovery, where if you have cluster is down, then you can use this deep store to recover the data and spin up a new cluster. Next, we have controller. So in controller is basically think of it as a brain of the cluster. So controller is responsible for managing the segments, doing the resource allocation. It is also responsible for doing table management, like table creation, schema creation, and it uses Zookeeper for a distributed coordinated service and use a Helix as a cluster framework. Then we have broker. So broker is like a query router. When the query comes, it hits the broker, and broker knows where the segment layout, and it knows which server hosts the segments, and it does a pruning. So in any query, it will hit only the server which are responsible for that query, and it will return the response. Basically, it requests the server for the data, and then once it get the data, return the response to the user. And so this is kind of a high-level architecture of Apache Pinot. And in the next section, what we are going to talk about is how did we move from Pinot local to remote storage. And if you see, there is no line from deep store to the query path, because initial days, deep store was only used as a disaster recovery or backup path. But when we move from Pinot local to remote storage, what we did is we used this deep store to in the query path, and that gives us a flexibility to decouple compute and storage. And my colleague here, Xiao, is going to talk about what we did and how did we optimize that path.
Thanks, Rag, for the intro. Yeah, from here, I'm going to talk about the how we implement tier storage. Basically, what is tier storage, why we need it, and how we implement that. Pinot was originally comes with this tightly coupled storage compute architecture. It was designed for serving low latency real-time workload. And we actually did a lot of design and implementation choice to make it really fast. And one of the design choice is this tightly coupled and storage and compute. So basically what it means is like each server, each compute node will have a local access to the disk and the SSD. And the access speed is super fast. It's just like micro to few milliseconds, and it is using POX's file API to access everything. But this comes to start to hit some limits when our customer asking for, say, they want to put more and more historical data in the same cluster. And meanwhile, they would like to still have this real-time performance aspects. So the data just grows far beyond what the local disk could handle. Because the storage and compute are coupled. So basically, if you want to more storage, you have to add more compute. And more often than not, those compute nodes you added are just sit there idle and kind of wasted. And that's why we introduced this decoupled storage and compute architecture. In this model, data instead lives in the cloud object storage for serving. And the cost of the cloud object store is far less than, let's say, for compare with the local SSD, is probably just like 1/5. But yeah, it comes with a trade-off, of course. Like the access speed comes to like 100 of milliseconds if we look at that, and compare with like micro to milliseconds before. And also it is like network calls instead of POX's APIs. But the benefits could be huge. Like the cost is far less than the local SSD, and also the cloud storage can be shared across multiple compute instances. It can be scaled independently by itself. So to put those two modes together, this is what we call the tiered storage. We still have the local tier that's serving the hot real-time data. But meanwhile, we also introduced this remote tier tenant, which serve the cloud object storage. And for that usually for the historical data. This way we have the flexibility of having just a single systems, but serving both your real-time data as well as your historical data, and you don't need to worry too much about the cost spiraling out of control. And as you can imagine, putting the data on the cloud object store instead of local is quite a challenge in terms of having a good performance, serving performance or query latency. So we need to answer two key questions here. The first is what data to read. Should we read the whole segments, or we can do better or more precise just to read a certain data that is needed. And the second question is when to read the data. Should we wait until the data is actually needed? Then we're going to fetch the data during the query execution, or we can do better to do some prefetch during the query planning. And first thing I want to, before jumping to the actual technique, first thing I want to mention is like why we don't do lazy loading. There is a bunch of query federation technique like Presto, Trino, or Spark out there. They're doing lazy loading, which is like the data that fetched by the initial query can be reused by the subsequent query. In Pinot's tiered storage, I would say at least for now, we are not doing lazy loading yet. And that's because in the Pinot, the query pattern is quite dynamic. Usually it consists of like a bunch of I wouldn't say random, but dynamic slice and dice and it is like a point lookup and dynamic slice and dice on various dimensions across timestamp or user's attributes. So more often than not, you are not able to reuse the data from one query to another, to the subsequent query. Another reason is lazy loading doesn't fully solve the problem on the initial query. So P99 or P99.9 could still be not very good. And in this case, we still want to solve or at least do something for the worst case scenario so that we can access the data with query latency in a fast and predictable way. So roughly to divide those techniques, we applied in when to read and what to read dimensions, but they are not completely independent, and we will get there once we work through each of them. So before jumping to that, I also want to revisit the Pinot format a bit because this is very important. Segment is the fundamental unit of how data is organized in Pinot. Each Pinot table consists of multiple segments, and within each segment owns a subset of rows. And within each segment, those rows are organized in a column format. So basically, each column followed by another. Let's say this table have several columns: browser, region, country, and you can see that with like the column is layout, one after another pattern, and within the column we actually have different index of this column. Forward index you can think of as the actual data, and if it is dictionary coded, we have dictionary. And also it could possibly have some specialized index like inverted index. And in this case, browser have forward index, inverted index, dictionary. There's two most important files for each column. One is called column.psf, which is like a single file that consists of all the data that belongs to these segments. And the other is called index map, which is like a metadata file that points to each of the start offside of each indexes. And when we do tier storage, we actually serve the column.psf directly from the Cloud Object Store. The index map, we pin that locally to the server itself because it is lightweighted. So with the column format, we actually can do better than just simply fetch the whole segment when we're serving this query. Let's say we have this query, select some impression where region equals to something. From the planning phase, we are able to know that we actually just need the forward index and dictionary on the impression. And for the region column, we actually just need the inverted index and also maybe dictionary. So we just need to fetch those indexes, and we use and we have the index map, so we know the exact range of those indexes, and then we just using a bunch of range get to get the precise range of those indexes instead of fetching the whole column.psf file. And actually, we can do even better than that. Like the idea is in some, let's say, some high selectivity queries, after the in-filter evaluation, we should be able to know that which documents actually matches this this filter evaluation. And yeah, like I mentioned the high selectivity queries, which means like the actual data matches is far less than the size of the forward index itself. So instead of fetching back the forward index, we can like just fetch those matched document in blocks, and that will be much less data than fetching back the forward index. Okay, and then let's go to when to fetch a bit. Yeah, like mentioned, Pinot work in segments, and let's assume that for these specific queries, we have 40 segments that are relevant to this query. So we're probably going to run the query against those 40 segments. And let's say we have 8 worker threads. So overall, we have 8 parallelism. And let's also assume that for each segment, it takes about 200 milliseconds to process, but the majority of the time might be fetching back the actual data that they need. The traditional way will be just processing the segment in batches, because you have 5 batches here, and each one takes 200 milliseconds. Overall, it takes seconds to get it back. But remember that we kind of already know that, let's say we already know those 40 segments are the relevant segments, even at the query planning phase. Then why we don't just issuing those requests at the query planning phase for those 40 segments? So that, I mean, best case scenario, let's say the request itself takes 200 milliseconds. It will just take 1 round trip to get them back, and so that it means only for the first batch it takes 200 milliseconds, and for the following 4 batches, you don't need to spend extra blocking wait time for those data to come back. So overall, the times could be 200 milliseconds and plus some execution time overhead. And similarly, we can apply this idea to the precise rate as well. So remember that we are talking about like after the in-filtering evaluation, we got a bunch of matched documents, and that's like sort of like what we do during the query planning phase. We can actually use issuing like some in parallel async IOs to prefetch those blocks immediately. There's no need to wait for the upcoming query execution to read those on demand. Then we fetch the block itself. So a similar idea we can apply to the post-filtering phase prefetch. So I think generally speaking, it comes to 2 ideas we apply. So first is like we want to saturate the bandwidth as much as possible, and also meanwhile you need to be mindful of what data you're actually going to fetch. It should be as much relevant as to your query. The other idea is like you'd like to leveraging async IO and some high concurrency requests to fetch those data back as early as possible. so that when the query actually need the data, it's better to be there instead of they doing some extra blocking weights. And lastly, I want to talk about the optimization, which is pinning index. So we actually provide another configuration to the user so that they can say that I want to pin some index on some columns specifically to the server's local disk, which is usually like a small disk. But everything else still goes to the cloud object storage. And for example, like user could pin the Bloom filter. And the idea is like you can pin those specialized index. It usually just consists of like a very small portion of the total storage you use, but it helps a lot when it comes to let's say you have a certain query that may leveraging these indexes. It will help a lot to speed up your query. And just to give you a brief idea, this is kind of like a benchmark we did on a small data set, which is about 200 gigabytes and a single Pinot server. As you can see, this query pattern is usually some aggregation with some filtering and maybe some group by and order by. But usually the query latencies we did can be among this 100 milliseconds latency matter order of magnitude. So to summarize, this is kind of like an evolution we did to make Pinot able to not only just read local data, but serving directly from the remote data. But still, it is on top of the Pinot's own specific segment format. And to leverage that, you probably need to go through some ETL pipeline or some transformation. In the next section, Raghav is going to talk about the evolution of making Pinot able to work directly on the open data format. Thank you.
Yep, you can. Yep. Thank you, Xiao. So we have seen so far like how we enable Pinot local storage to remote storage, and we have done a bunch of improvements to optimize access to object store and make queries faster. But one of the key constraints is you will have to ingest the data into Pinot format, and then only you can leverage this query engine. So next natural question, given the popularity of open data format and as they are becoming central to any data infrastructure, how can we bring this query engine and all the optimization we did on the data lake? And that's the next section, basically what all we did. And one of the key things was Pinot was designed from the first day, and hats off to the creators that they thought and made the system so pluggable that plugging any new format or any new table or data format or table format is very easy. And other key thing is like you don't need to do a data duplication, because as of now, if you have to bring your data lake into Pinot, you will need some ETL job and copy the data into Pinot format. And with the support of open data format, you will not need any data ETL or data transformation. So if you look in the diagram, so what do we do? So what happens is like you do a remote Parquet registration into Pinot. And what does it mean is it instructs the system to create a metadata thing, and it is a pseudo segments. And if you see in the diagram, the yellow part is the segment metadata, but the Pinot server boxes are empty, which means we are not storing any data. And what we have is only metadata and the indexes, which you have configured. And now you can access the raw Parquet files, or you can query the iceberg table itself. So what does the metadata look like? So if you look into the metadata, what we store is the location of the Parquet. So you do see there the S3 location. It's a pointer to the data file. and then we store when the segment was created, what is the segment CRC, and the size here represents the metadata in the indexes size. So you really don't need a lot of storage to run this query engine, and you can build new indexes, and then you can delete those indexes. You can do all those interesting things to run the query much faster. Yeah. So how many of you have worked with Parquet or are aware of the Parquet file format? So yeah, a lot of hands. So Parquet is a very popular format, and it has been ruling the data format. And just to recap, the Parquet is a columnar storage format where the data is laid out in the columnar fashion. And the key things here are like it has a concept of row groups to minimize the disk access. It has the concept of pages, and page are the fundamental unit of disk access. So if you have to read a record, you have to do minimum page read. And there are few challenges, like if you cannot read directly a page, you have to serially go deserialize and access the page one by one. So that becomes an IO bottleneck, and we'll see how did we optimize that. And yeah. So just to recap the Pinot segment format. So left-hand side is where the Pinot local format is, where we have the forward index, inverted index, and dictionary. And the right-hand side is the remote Parquet, or this is the pseudo segment. So top part is the Parquet file, which is sitting in S3. And we just have a pointer into the Pinot segment. And there are additional indexes like inverted index, range index, which helps you speed up the query. So as I was mentioning that what we did is we tried out a lot of Parquet readers out in the field, and what we found is there were few bottlenecks, and we wanted much better. So what we did is we built our own custom Parquet reader, and few things we did. So we built a multi-level caching. So the caching, basically, what did we need to cache? So first was the metadata cache. And every time you read a page, you will have to go to the deserialization process. So we even cache the page metadata, so that whenever we have to fetch a page corresponding to a doc, we don't have to go through the deserialization process. And we also, and if you have worked with a data system, you know serialization and deserialization is one of the most like bottleneck part of the performance. What we did is we not only cached the byte raw data buffers of the pages, but we serialized them into and kept into the row format. So whenever the query is coming and if it is hitting the cache, then you can literally get the query latency in milliseconds. Yeah, so we will go through the same questions we answered or ask ourselves when we enable Pinot local storage to remote storage. So first is what to read. So if you see this Parquet file layout, imagine you have 3,000, or in this case, there are 2 row groups. So imagine you have 10,000 documents, and when you are running a query, you want to fetch only few documents. And the green part shows the document which we are interested in is part of those pages. And when we have to fetch, we just want to fetch those pages. But a lot of readers, what they do is they fetch the whole column chunk, and which is a waste of data. And knowing S3, like you can do data reads at petabyte scale can really cost you not only the pricing, but also the performance. So what we do is we have a mechanism using our metadata where whenever the query comes, we apply the filters. We know which doc IDs we have to fetch, and those doc IDs are translated into one of these pages, and then we fetch only those pages. And we also have the cache. So next time if the query is coming and the filter operations are not changed, we will leverage the cache and the query will be much faster. Yeah, so next question is how much to read? So Parquet has some inbuilt indexes. So what you can do, so Parquet has this min and max on the column, and that is at the column chunk level as well as the page level. And you have dictionary filtering and the Bloom filters. But these are very basic filtering mechanism. Generally, when you are building an analytics system, you need much more advanced indexes. So what are the things which are missing? So this is at the file level. So you cannot do a file level skipping. Range or timestamp indexes are not there. So for example, if you want to query last 1 hour data or last 1 day data, then those kind of filter you cannot apply. And then there are no complex filter or partial matches. For example, vector search, if you have to build a vector search on top of Parquet files, or if you have to build a text search on top of Parquet files, so you cannot leverage these indexes. So what can we do? So Pinot's superpower, if anyone asks me what is the best thing about the Pinot, so my answer always has been the indexes. And these are all very powerful indexes, and they are mini DBs within database itself. For example, inverted index, you can do a point lookups. We have a vector index where you can do the vector search. A star tree index where we can run the aggregation index. We have geo index as well as the JSON index. So the next question is how you can apply these indexes on top of the Parquet file, and that's where the concept of external indexes come in. That whenever we do a registration of this Parquet file into Pinot segment, then as per the table configuration, whatever the indexes are configured, we will build those indexes and keep into the Pinot segment metadata for the queries to leverage. So next question is how do we speed up the reads? So we will again leverage the two key things. One is async IO, and the next is leveraging the indexes and Parquet metadata cache. So this is at the high level how whenever you run a query, for example, we have this aggregation query which is running with the filter browser is equal to Chrome. So in query, it goes through a query engine. First it does a planning, and then it applies a filter and the projection. And we have some smart indexes like a sparse index, which at the planning phase itself, while we are applying the filter and other indexes, we can figure out which blocks we want to fetch from the object store, and we can trigger them in parallel while we are going through the other operators. Filter operator is basically the indexes which we saw that we want to filter based on inverted index or a JSON index or a search index. You would be able to filter those. And then finally, once you have found the records, then you can apply the projection and fetch just the blocks you are interested, which will be the pages which we saw in the Parquet file. And next concept is index pinning. So this is more of an index cache, which you can build locally. So it's a metadata. So one option is you always go to the cloud and you retrieve that. Other option is you can have those caches locally, because most of the user-facing queries, they repeat a lot of predicates, a lot of filter operators. So there is a benefit of storing them as a cache. And what you can do is basically once you pin the indexes, then whenever the next time filter operation is happening, it will fetch those index from the local disk, and it will be much faster. And other thing which we do in parallel is while we are doing the filter operators and other operations, we have some smartness in the forward index, which enables us to parallelly fetch the Parquet blocks. And in object store, if you see, we have Parquet files and Pinot indexes as well as the local. Yeah. So now the next question is, how do we integrate into Iceberg table? So we saw how did we enable the support for raw Parquet files. Next question is, how do we integrate into Iceberg table? So if you see the architecture, we have a table creator and Iceberg watcher task, which is listening to or connected to your Iceberg table format. And basically, it is doing two things. It is first finding out the schema. And once it has identified the schema, it automatically creates the table. And it is constantly watching into the catalog to see if any schema change has happened or any change in the configuration has happened. The second thing is it is going through the snapshot IDs, and each snapshot ID tells you what are the files which is part of that snapshot, which points to the Parquet files in S3. And once you have that file, then it will trigger a process to ingest that Parquet file into Pinot. And what this mean is it just create a pseudo segment with the metadata and indexes inbuilt. So basically, the journey started with a local storage where you need a very tightly coupled compute and storage, and because you are always bounded by the disk. And as the data is growing, now you have a petabyte scale need, and a lot of times you just want a cost-effective storage. So then we moved to the remote storage, but then we saw that customers still have to do this ETL transformation, and anyone who has managed the ETL pipelines knows how complex they are. And it seems very simple at the beginning, but it grows really complex. Then the next evolution is basically there are a lot of open data formats already the right path. So our goal is to just bring all the good like Pinot-related query engine or Pinot query engine on top of the data format. So this is what we did as part of the evolution. Now, what it has given us the flexibility of how you can use this in a different variety of form. So if you see, this is access source like the performance of performance and the cost. So if you are very performance sensitive but don't care about the cost, you can start from the local Pinot index. If you want to have the Pinot index but you want a S3 Parquet files, and then you can move to the bottom, which is the slowest in this diagram, but the most cost-effective one, where you can have everything remote in S3. So what it means is, and you don't have to do any data movement to toggle these things. These are just a simple table configuration change into Pinot, where you can change the table configuration, and behind the scene, configuration will be all automatically applied. So there could be a window where you want a very highly performance system and don't care about the cost, but there could be months where you just want everything to be coming from S3. So these are all the configuration allowed. And so that's all we had for the talk. And this is the resource. You can scan the code, and we have a lot of interesting engineering blocks where we have been talking about all the innovation we have been doing. Yeah, thank you. Thank you so much. Any?
Thanks so much for that talk. Up next, as I already said, we have Owen on VeloDB. Please come. Okay. And now I get to walk around the stage and fill time while the computer gets plugged in. Seen any good movies lately? No, we're not going that. We're not stooping that low.
Okay.
Almost. All right. Take it away.
Okay. Hello, everyone. I'm Owen from Apache Doris community, and I'm a PMC member of the open source project, and I'm also a co-founder of VeloDB. The company is support commercial products based on Apache Doris. Today, I will talk about semi-structured data analytics. We've discussed approaches from text to JSON to variant. Before I jump into the semi-structured data, let me introduce Apache Doris briefly. So, how many people who knows Apache Doris? Please raise your hand. Oh, a few people. I think that I should not introduce Doris briefly. I should introduce it in detail. So I'm in the right place here. Okay, Apache Doris is an open source project, real-time analytics and search database. It was first created by our team at 2013 in Baidu, the second largest search company of the world. It was then open sourced at 2017 and contributed to Apache Software Foundation. It graduated to be a Apache top-level project in 2022, the year that we started the VeloDB company. The Apache Doris community is very active, so let's see some numbers. That you can see that more than 14 Kino plus GitHub stars, 699 contributors, and I hope it's a quite strange number. So I hope that one of you may be the lucky 700th contributor of Apache Doris. Yeah, and among all the Apache projects, including Apache Spark, Flink, Kafka, and others, the number of page views of the official website of Doris is the highest, and the monthly active contributors is also the highest. So welcome to our community. And not only Apache Doris is popular in the developers, it's also very popular used by the companies. More than 5,000 companies are using Apache Doris in production environment. So why they choose Apache Doris? Let's say a real user. This is, I think, the answer from the real user. He said that why you need Doris, since it's very real time. It can, if your dashboard need refresh in real time, not in 15 minutes or even 5 minutes, you can use Doris. If you want to handle complex queries, especially join queries for analytics, you can use Doris. And Doris can handle more than 1,000 concurrent queries without breaking. And it also cuts the cost by more than 60% than other cloud data warehouses, such as Snowflake. So compared to other systems, for example, compared to Snowflake, real-time ingestion instead of batch ingestion, so the latency drops from minutes to seconds. And compared to BigQuery, the queries are very faster. It can be second or even sub-second. And compared to ClickHouse, Doris is much better for mixed workload. It's not just fast for wide table aggregation, but it also supports complex queries, full text searches, and vector search. Yeah, and there are many use cases that can be suitable for Doris. So, let's focus on today's topic, yes, the semi-structured data analysis. I will talk about the characteristic and the challenges of semi-structured data first, and then see the different approaches to address these challenges, and including the systems like Elasticsearch, Snowflake, Apache Doris, ClickHouse, and Iceberg. And then I will show the usage of Apache Doris variant feature and what's the typical use cases. So let's go ahead. As you know, that in data field, we classify the different kinds of data into structured, semi-structured, and unstructured data. The structured data is very frequently used, such as relational table. The semi-structured data have flexible schema, such as JSON and XML. As you know, JSON is very popular in recent years due to its flexible schema. And for unstructured data, such as text, video, image, they don't have a consistent schema. Okay, so when we talk about semi-structured data, what are we actually talking about? I find the explanation from Wikipedia, and I think it's just sounds reasonable. It says that semi-structured data is a form of structured data that does not obey to the tabular structure of data models and other things. I think you can find it and follow the link below. Yeah. As a conclusion, I summarize the 3 characteristics of semi-structured data that distinguish it to other kinds of data. The first one is that it doesn't adhere to the fixed tabular structure. And the second is that instead it still has structure, yeah, but it's not a fixed structure. It's self-describing and non-fixed structures. Yeah, and the last is that hierarchy are very common in semi-structured data such as JSON. So according to the characteristics of semi-structured data, there are some challenges for this kind of data. Yeah. The first is schema flexibility, since the fields in JSON will be add or remove any time, and the data type of a single field in the semi-structured data will change over time. Yeah. And the second is for storage efficiency, how to improve the compression ratio, and how to make read and write throughput much higher is also challenging. And the third is that the analytical performance for filtering from many rows and a large number of rows and aggregation over a few number of columns. It's very challenging. Yeah, let's see some different approaches to address these challenges. Here I will put some major category of challenges in the coordinate system. The horizontal X is about schema flexibility. Yeah, since the schema flexibility is very important for semi-structured data, and vertical X is about performance. Let's see the first two naive approaches. They are in the left up and right bottom columns. ETL approach will ETL extract the columns by the ETL pipeline and store them to the structure table, right? So it's the performance is very high since they are structured, but it's not flexible. If the new columns are added to the source data, the ETL pipeline needs to be adjusted, and the table structure, table schema need to be altered. So it's not flexible at all. Yeah, another approach, the JSON string. Yeah, you can store the whole JSON in a string column, right? Yeah, it's very flexible. You can store any kinds of any different structures JSON in a single field, but it has poor performance. Since if you need to analyze one single field in the JSON, you need to read the whole JSON from the storage and pass the field that you need from the JSON string. As you know, the parsing from string is very expensive. It's very slow for CPU. Yeah, so a very straightforward optimization appears. The JSON binary JSON, yeah. So passing JSON string is very expensive. So can we pass the JSON string once on ingestion and store them as in the binary format, which is more compact and more easy to use on query? Yeah, that's just MongoDB Bison and Doris JSONB does. Yeah, it's faster, typically 2 to 4 times faster on query than the JSON string, but it's still not fast compared to other approaches. Recent years, another approach I called variant-like approach is gain its popularity, and the main strategy is that automatically parse the JSON and extract the fields from JSON and store them as separate columns instead of one JSON string column. Yeah, separate columns, maybe 10, 100 or more. Yeah, so it's very performant. It's very performant since you can use column storage for each subcolumn, right? If you want to analytics or filter on a single column, you just read the columns that you query. Many systems like Elasticsearch, the dynamic mapping feature in Elasticsearch use this approach. Snowflake variant data type and Doris variant data type, ClickHouse JSON data type, and the recent Iceberg v3 variant data type are using this approach. This table summarizes the comparison in detail what I talked about. Just I talked about. Yeah, one thing I want to emphasize that. So it's very good. It sounds very good for variant data type. So what's the disadvantage? Yeah, there is no free lunch, right? Yeah. I think the disadvantage is the complexity. It's very complex to implement. But you may ask that, just extract the columns from the JSON and store them as separated columns using in the column storage format. It's quite simple and straightforward. So what's the complexity? So let's go ahead and see what's the complexity. Yeah, it comes with skill and other things. I think there are 4 kinds of challenges in implementing a very performant, variant-like approach. The first one is too many columns. Just imagine that. How about if you have 1,000 columns, or even 10,000 columns, or even 100,000 columns? There will be many columns in the system. As you know, if you have too many columns in the column storage system, it's not okay. It's just not okay. And the second challenge is that type evolution. You know that in JSON, a single field the data type will change over time. So if the time changes, what's the exact data type for the extracted column for the field, right? It was int, and now double, and in the future string. What's the exact type? You know that for a database, you have to define a type for the single column. And the third challenge is that indexes. Indexes are very important for query acceleration. So what about indexes for the extracted columns in variant? And the last one is controllability. Yeah, I think the automatic inference is very good. It's a good approach, but it's not always right. For some complex conditions, it may cause poor performance. So can the system let the users to specify some concrete data type or even types is important for the users. Okay, let's go into details about the challenges and how the system, as I mentioned, they deal with the challenges. For first one, for too many columns, how the system deal with it. Let's see Elasticsearch dynamic mapping at first. It has a limitation to 1,000 columns by default. If you have more than 1,000 columns in your JSON that you try to ingest, it will reject the write request. So it may cause data loss in some cases. I think it's not acceptable for the database system. Yeah. And the second, Snowflake variant data type, it also has a limit to 200 by default. And you can, in that document, they say that if you want to increase this limit, you can contact the support team, right? So by default, 200. Yeah, but Snowflake will not reject writes or lose data if you have more than 200 columns. It just stores the existing fields into a combined column. So if you have 203 columns, you will end it up with 200 separated columns and one combined columns for the 3 exceeding columns. So it's okay. It will not cause data loss, but the performance of the exceeding fields will be much worse than the extracted ones. Yeah, and for Doris, we follows the approach that Snowflake used, but we increase this limit to 2,000 by default, and some users even test up to 6,000 or 7,000 columns in production environment. So I think the higher the limit, the better for the users. Okay, and for CleanHouse, almost the same approach with 1,024 by default. And for Apache Iceberg and Parquet, I didn't find the definition in their specification since they are still in under development. So I think it's an open problem for them. And for the second challenge in type evolution, how the system deal with it. Yeah, for Elasticsearch, it's very simple. Yeah, the data type for a field is determined by the first time that is ingested. So for example, you have a column A with the data type int at the first time, and then you want to ingest a JSON with the column A in type double. It will reject the write request. It still cause some data loss problem. So I think it's not acceptable for some rigid cases. And for Snowflake, it has another approach that you can write the data into it with different types for single column. But for this kind of column that the data type is not consistent, it will not extract the column from the JSON and will store them as a combined column. So the performance will decrease. And for Apache Doris variant data type, a single field can have different types in different data files, since that they don't affect each other. And in a single data file, if the types of single column is not the same, a type of promotion will be made for this column. For example, if you have int and double, they will promote to double. Yeah. So the performance will be better even in this kind of we call type evolution or conflation. Yeah. And for ClickHouse, I think almost the same approach. Yeah. And for Iceberg, still not defined since they are in development. And for third challenge, indexes, how to index the extracted columns in variant. I think Doris did a very good job. Elasticsearch is very famous for its search and inverted index. So it provides inverted index and even vector index for the extracted columns. And for Snowflake, it supports a so-called search optimizing index in recent 1 or 2 years. Yeah. It supports acceleration for echo, substring, and geo queries. And for Apache Doris, we support inverted index, vector index, Bloomfield index, min-max index, and many others. And particularly, we have a feature that we call index on demand. If you have 100 columns, and you don't need to define all the index at the time that you create the table. You can just, for example, just define 10 index for the 10 columns. And when your business changes and your analytics requirement changes, you can add more index. For example, add another 5 index on demand. It will not rewrite the whole table. It's very useful for the businesses that are changing and evolving faster. Yeah. And for ClickHouse, it just supports Bloomfield and min-max index. And for Iceberg, not specified, I think. So one key point is that Doris supports most types of indexes, and it's very important for high concurrent queries, very important for full text search and vector search queries. It is very flexible for on-demand indexes management. Yeah. And the last challenge for variant-like systems, how to let users specify schema for fields. I think Elasticsearch did a good job for that. It provides a mechanism called dynamic template to specify the data type and the index of a field by its field name or field pattern. Yeah, I will give some example in the next pages. And Doris follows the approach of Elasticsearch and provide a similar mechanism called schema template. Users can specify the data type and the index by field name and the patterns. For example, the golf match patterns. So users can control the behavior of the inference from JSON fields. And ClickHouse provides some simple mechanisms. The user can specify data type by field name. Imagine that you have hundreds of thousands of fields. It's very hard to define the field, the type by field name one by one, right? Okay, after we explore the challenges that a different system, and we can see the performance. Yeah, we compare the performance of Spark with Iceberg, and Elasticsearch dynamic mapping, Snowflake variant data type, ClickHouse JSON type, and Doris variant data type. We use the test data from Blue Sky datasets with 100 million records and about 1,000 columns in the JSON field, in the JSON data. Yeah, as we can see, that Spark is still under development. So I think they haven't finished the column storage for the extracted columns from JSON. So it's much slower. But for the other 4 systems, we can see that among the 4 queries, the 5 queries, the 4 of them, Apache Doris is the fastest. Okay, let's focus on Apache Doris variant, the usage of the system. How it is simple, it is very powerful, right? And it's very fast. So is it very complex to use? I think it's no. It's very easy. Let's see the first how to define the create a table. We see that we have 3 variant columns: actor, repo, and Pinot. For the simplest columns, you can define the variant column just actor, repo. They are variant fields without schema template, or will be automatically inferenced by Doris system. And for the Pinot field is more complex. So it's the schema template feature that I mentioned before. Yeah, you can for example here you can define the field start with Boolean, use the data type Boolean. The field start with string, use the data type text. And then you can define text schema template for index. For example, the most interesting one is the last 2. You can see that we define 2 indexes for the fields that start with string. Yeah, the one index is for exact match, non-tokenized index in inverted index, and the last one is a tokenized index or full text index that will be analyzed or tokenized by Unicode. So it can be used for the match queries. Okay, let's see so after you define the table, you can list the structure. Yeah, the table structure, table schema will evolve over time. If you just describe the table, you will get a normal output as other tables. But if you set a session variable, describe, extend the variant column to true, you can get the subcolumns that extracted automatically by Doris. For example, actor.id, actor.url, actor.login, and some others. And at last, we see the query. Yeah. So the first is a very simple one. You count the GitHub events table, and you for the rows that Pinot actor ID equals to my ID. The syntax is similar to the map syntax, maps data type. Yeah, it's very simple. Yeah. The second query is more complex. You can use match keyword for the Pinot comment body column over the Doris keyword. It's just try to find the most recently 100 comments from the GitHub table that have the keyword Doris. It's very simple, right? Yeah. At last, I will share some typical use cases in a real environment. The first one is log and trace data in observability. One of the major use cases for Apache Doris is observability. Many users use Doris to store the log, trace, and metrics data for monitoring and observability. As you can see, some log and trace data has extension fields. For example, the ext field in this example, you can define the ext field as a variant. It will expand the subcolumns as the data ingested. For this use case, the benefits are first, it allows for field type changes avoid data loss, since the producer of the observability data will not notice the DBA that we have changed the data in the extension field, so the system can deal it automatically. It will automatically add and refuse the fields in the schema. And for cost, it will achieve 5 or even 10 times higher compression ratio compared to the raw JSON string, since they use column storage. And the second use case is about Internet of Things or Internet of Vehicles. the device data often contains some text. The texts are not fixed. The fields in the text are not fixed. So you can define the text column as variant. And you can filter on it. And you can run the array functions such as array contents on the subfield of the tag column. You will get some benefits. The first one is the very high analytical performance, since all the fields in the text are extracted as separate columns. And it can support thousands of columns for tag evolution, since the text in the IoT and IOV systems will evolve over time. And the same, the compression ratio is very high. It means no cost. And the last use case I want to share is from the SaaS application or SaaS companies. Many SaaS application companies provide the mechanism to let their SaaS users to define their customer properties, and it's very flexible for their users. And it's very useful, and you can define the properties column with data type variant in Doris, and you will get the benefits that thousands of fields for customer properties, and your customer will like it very much. And Doris supports rich index and high concurrent queries in most SaaS companies. The customer-facing analytics is very important. And there are hundreds of thousands of users using the system to query data. And the last benefit is Doris supports both full text search and joins. As you know, Elasticsearch is good at search, but it cannot do joins. And many database systems good at joins, but search is poor. So Doris, I think, maybe the one of the most important systems that support both search and joins. Our customers said that it's the reason that they choose Doris. Okay, that's all. So welcome to Doris community. As I just mentioned, we have 699 contributors in our community. I hope that one of you will be the lucky person to be the 700th. Okay, you can join our Slack for discussion, and follow ValueDB LinkedIn to get most recent news and technical articles about Doris. Okay, thank you.
Thank you very much to all of our presenters today. I won't keep you here much longer. I'll say thanks again to Adobe